Bismillahirrahmanirrahim. Assalamu alaikum everyone. Today we're going to be learning lesson number 34. It's a small lesson. It's the end of trigonometry. It's called the area of a triangle. So you might be looking at this going like, I thought we already knew how to find the area of a triangle. It's sort of different because we use trigonometry to actually work with it, inshallah. And at the end of this, there's going to be a small little homework assignment that I will be assigning to you as well. Okay, just looking forward. We're going to be starting with Algebra 2 Advanced very soon, and we're going to move over to Stats and Probability, and we're going to end, inshallah, with Calculus. Those are 3 lessons of Calculus right there. Okay, so let's go ahead and start. The first thing that I did is I pulled off from the Important Concepts page. I'm sure everybody's familiar with that now. It is on the website. I pulled off a little portion of it that I think is going to be relevant in today's lesson. And the first one is the law of sines and the law of cosines. Well, that more is relevant to the previous lesson, but that might come in handy today, may or may not. But something that goes right hand in hand with it, and you want to write down in your notebook, is the area of a triangle when you're given side angle side. Recall that the law of sines and the law of cosines had certain uses to them based upon what was given to you. So in the same sense, in an area of a triangle, if you're given a side and another side and an included angle, you're going to be able to use the formula that's right in front of you right here. Okay? The A and the B are both sides, just like they were in the law of sines and the law of cosines. And the sine of C is the same angle, sine the same angle as it was in the law of sines, all right? So it's basically using the same things that you could have derived from law of sines and cosines, and it's finding a really cool technique to actually find the area of that triangle, okay? And the other one, which is a very interesting one, we still teach it though, is called Heron's formula, right? The Heron came up with a very interesting technique of finding the area of a triangle, and he said, I don't need bases, I don't need heights, just give me the length of the 3 sides, and then he gave us a formula. I will be showing you how that formula works, but you want to familiarize yourself with how it looks though, right? Notice how the area of a triangle is written as K, and it's because we don't want to confuse A with the sine of A, right? So, with angle A basically. So we just call it K in this textbook, right? So let's go ahead and get started, inshallah. I'm going to take number 6 first, and I'm going to try number 6 with you guys. In number 6, think to yourself, which formula for the area of a triangle, because we need to find the area of each of these triangles, which formula for the area of the triangle would work best here, right? You don't have all 3 sides given. What you do have given is a side, an included angle, and another side, right? So the included angle is because it's between the 2 sides. So it would be best to use the first formula. K is equal to 1/2 the 2 sides, 3 times 4, all right? And then the sine of the included angle. And the sine of the included angle is 30 degrees. So that's pretty much it. You just plug this into a calculator and find out what that's going to be. If you don't have access to a calculator, you could try simplifying, because we do know what the sine of 30 is, right? The sine of, bismillah, 30 degrees is opposite over hypotenuse. So I believe that's a 1/2, right? So that'll become 1/2 times 3 times 4 times 1/2. So essentially, you're looking at an answer of 3. So that's the area of that triangle. And realize that that's very profound, because now you don't need to know the height of the triangle. You don't need to know necessarily its base. Here you coincidentally have its base, but you don't need to know either one of those. As long as you have a side and an angle and a side, you actually can find an area now. Okay, so it's an interesting technique that has been given to us. All right. One thing I will mention though is if you had a right triangle, right? If you had a right triangle, there's a 90-degree angle. Let's suppose I told you that this side right here is 3, this side right here is 4. of course, you can make that deduction that the hypotenuse should be 5. If you said, why can't this formula work on a right triangle? Guess what? It can. 1/2, right? 1/2. I'll use this as the included angle, so I'll use the two sides. So side, angle, side. So it's really cool. Just check it out. 3, 4 are the sides, and the sine of the included angle. Now what's the included angle? 90 degrees. And what's the sine of 90 degrees? It's 1. So this problem actually just becomes 1/2 times 3 times 4. And you might argue, wait a minute, isn't that the same thing as 1/2 base times height? So that's actually why the formula that's over here is not too surprising to us. When you don't have a 90-degree angle, that's okay. You can still solve it using this really cool trigonometric formula that is a variation of the regular formula you've been learning for so many years from middle school. All right? Let's try a second problem, which is number 10. And in number 10, basically what we're going to do is we're going to use the idea of a side and a side and a side being given to us. Notice how we're not trying to solve for any angles here, okay? Our job is to solve for the area of the triangle. I know that all these shapes look exactly the same as the previous lesson, which was the law of sines and cosines, but that's not what we're trying to do here anymore, right? So here is what the formula, also known as Heron's formula, is a story to it, but you know, I want to keep these videos short, so unfortunately I can't share that story today. But basically, you're supposed to first find something called S, right? So step one, you need to find S, and S is the addition of all the sides. So add up all the sides that have been given to you, and they must be given to you because that's why you're using that technique. And when you add up all the sides, you end up with 11 in this situation. All right. Then step 2 is you need to go ahead and take that amount and divide it by 2. You know, so why did I circle that just now? That was not a good idea. So, okay, so you basically take, that's not step 2, that's just the same thing. So you divide that by 2. And again, if you just look at the formula, you'll understand where I got that from. So this is going to give you 5.5. All right. Step 2, you take a look at Heron's formula, and Heron said that the area can be found by taking a massive square root, so a massive square root of S, so S is 5.5, multiplied by S minus one of the sides, all right, so like that, times S minus another one of the sides. By coincidence, both of those sides are the same. That's okay. Not a big deal. All right. And then finally, multiplied by S minus the third side. And the third side in this situation was a 3. All right. So 4, 4, and 3, I've highlighted them for you in red so you can see where I'm getting that from. And he said that this will give you the formula, that the area of that triangle. All right, so I leave that to you. You guys know how to work with, you know, plugging things into a calculator. You can simplify it a little bit before you plug it in, right? So those are 1.5s. This is a 2.5, but it all just basically goes in your calculator, and you can find an area of the triangle. All right, so that's objective number 1. Objective number 2 is for us to do some application problems, inshallah. All right, so here's one for you. The area of something called a segment. All right, so we're going to be drawing a circle here. All right, let me quickly draw a circle, and then we'll put things that the problem is talking about into the circle. All right, so it says find the area of the segment of a circle whose radius is 5 inches. So let's start off by just roughly drawing a 5-inch radius over here. And it forms a central angle of 40 degrees. So here is 5 inches as well. Oops, sorry. Apologize. Let me just turn this off real quick. All right, so this is also 5 inches, like that. And you have a central angle of 40 degrees. Now, here is a way to misunderstand this that says segment. It does not say sector. Okay, it does not say sector. If it had said sector, that would have meant that we find the area of this entire piece of the pie, right? That you've learned in a different part of trigonometry that I've actually taught you, right? So what they're really interested in is the following, right? They want you to find the area of this part over here. And if you didn't know that from before, if you're like, wait, that's what a segment means, so that's news to a lot of people, right? So that's actually what we're trying to find the area of. What is that area equal to? All right, so now I want you to think about what have you learned in this lesson that can help you. And what we can basically try is, here's the logic. We'll find the area of the sector, all right? And then we'll subtract the area of the triangle. Notice how there's a triangle that's formed. If you ignore the segment, here's the segment, here's the entire sector. If you ignore the segment from the sector, you'll notice what you've essentially made is a triangle, right? So what we're going to do is first let's find the area of the sector. Now there's a couple of ways to do this. You can go back to the previous lesson where we learned to find the area of a sector. If I'm not mistaken, the area of a sector can be found by doing 1/2 r squared theta, all right? Let me just check that really quickly. So you can use this formula and it will help you find the area of the sector. There's just one catch. You got to make sure that theta is in radians. If theta is not in radians, then it's not going to work for you. Now, while we're here, and most of this lesson is not discussed in radians, it's in angles, right? We might as well just stick to angles, i.e., we'll stick to the way that we used to do this in geometry. Okay, so let's go back. To find the area of this sector, what you can say is, I know that the area of a circle is pi r squared. So if I need a area of a sector of a circle, it'll just be whatever amount that sector is, let's call it x, divided by 360 degrees, multiplied by the area of the circle, so pi r squared, right? So in this situation, we've got 40 degrees. And you know what? This is still the way that I generally tend to do it. Despite the fact that trigonometry has this formula for area of a sector, I don't really much use it unless I totally have to because theta is given in radians, right? So if you don't understand what just happened, when theta is given in radians, you basically use this formula. When theta is given in degrees, just stick to the one that you learned in geometry because that's what you learned in geometry to work with degrees, right? So I'm using this formula right here. So 40 degrees divided by 360 degrees multiplied by the area of the entire circle, so pi 5 squared, and that'll give you the area of the sector. Now let's subtract the area of the triangle. Now the area of the triangle, this is where the lesson that we learned just now, it comes into play. What we can do is we can use that formula that we established, 1/2 5 times 5, and then the sine of 40 degrees. Now, this may be still new to you, so let me remind you, side, angle, side, right? You have side, angle, side. You can use this really cool formula for the area of a triangle, and it'll get the job done for you. And once you run these numbers, it's going to give you the area of the segment, right? So that's objective number 2. All right, let's go to objective number 3, inshallah. All right, number 39. So this question says that you basically have a circle with a radius r and a center O. So I'm going to go here and I'm going to label these as radii r, okay, and a center O. It says find the area K of the shaded region. So K is basically the entire shaded region as you're looking at, as a function of the central angle theta. All right, so that's what the question is asking us to do. And you can do this in different kinds of ways. All right, there isn't one specific answer. but here is one way to go about it. All right, so what I can say is I will find the area of this triangle over here. All right, so you guys are seeing me highlighted in yellow. So let me find the area of that triangle. Then what I'll do is, I don't know if this green highlighting will work well on this, but then I'll find the area of this sector, right? That's a sector right there. And if I just add them up, I'll have the area of the shaded region. So that's what I'm about to do. All right, so one thing we got to do before we start, though, is we got to tell things in terms of the central angle theta, right? So if this central angle is theta, what does it make, Bismillah, this angle over here, right? What is that angle? Think about it. There's a whole straight angle here. We've been given that that's theta, and so you should have thought to yourself 180 minus theta, right? In degrees, of course. All right, so let's go ahead and set something up. All right, first what I'll do is I'll talk about that triangle. All right, let's talk about the area of the triangle. Remember, everything is going to be abstract here. They don't necessarily have numbers. So using that formula that we've learned in this chapter, we can say 1/2 the two sides that are opposite or on adjacent sides of the included angle. So r and r. I know that that's r squared, but I just want to specifically write it in the format of the formula for now, times the sine of the included angle. And what's the included angle? The included angle is 180 minus theta degrees. All right. So that's what that area is going to be for the triangle. But now let's talk about the area of the sector. Okay, the area of the sector is the part that I've highlighted for you in green. Well, the area of that sector, using the same exact logic as we did in the previous example, I can say if I have theta, I can divide it by 360 degrees. Remember, theta is given in degrees. And I can multiply it by the area of the whole circle. And the area of the whole circle would be pi r squared. So once I get those two things, I will have an answer. And the problem wanted to find the area of the shaded region as a function of the central angle. So now we can write down an equation for k, right, which is area. And that's essentially the area of the triangle plus the area of the sector, which is going to be k is equal to 1/2 r squared sine 180 minus theta in degrees plus theta over 360 degrees times pi r squared. Now, if you were to look in the answer key, it might look a little bit different, but that's not something we're necessarily concerned about. What's important is we've got a formula that actually works for us, okay? If you would like to think of a second way, by all means do so, right? You are a class that generally likes to think about different alternatives. But here's one thing I could tell you, is what if you found the area of a semicircle, right? And that would be 1/2 pi r squared, and then found a way to subtract the area of the segment that's been created. That's not shaded, right? It's the non-shaded segment, right? So if you could find a way to find the area of this non-shaded segment, right? I'm shading it for you just so you understand. Then you could subtract that out, right? You could subtract that out, and you could come up with another formula. But just thinking about how you get to the area of a segment is done in a specific way, as we just highlighted over here, that might be more work than we really need to. But there you go. That's one of the ways that you can come up with the formula to find the area of the shaded region as a function of the central angle that you're looking at. All right, that's essentially all there is to this lesson, believe it or not. Inshallah, you'll pick it up just fine. I've left about 4 or 5 questions in the homework for you guys to try. And good luck and Assalamu alaikum.